Welcome to the Explainer. Okay, we're jumping straight into crushing your chemistry exam today by mastering what is essentially the ultimate molecular toy box. If you've ever felt completely overwhelmed by organic chemistry, well, get ready, because we are going to break it all down visually, and it's going to make total sense. I want you to think of polymer chemistry not as this giant list of abstract, impossible-to-memorize formulas. Instead, it's just a huge set of snapped-together building blocks. It's like a giant puzzle. And just like with real building blocks, once you master a few super simple rules for connecting them, you unlock absolutely infinite structural combinations.
And what's really fascinating is how this specific chemistry grounds us in reality. It reminds us that literally everything around us, from the heavy bitumen on the roads we drive on, to the plastic wraps sitting in our kitchens, right down to the synthetic fibers in the clothes we're wearing, it all relies completely on these tiny engineered chemical connections.
So, here's our quick roadmap for this crash course. First, we'll cover the rules of the toy box. Then we'll look at the nylon blueprint. After that, biodiesel from fats. And we'll wrap up with the polyethylene paradox.
Starting with Section 1, the rules of the toy box. Let's lay the foundation.
Okay, this right here is an absolute must-know definition for your exam. A macromolecule is simply the finished, massive structure that you build by linking together countless tiny, repeating individual units. And we call those tiny starting units monomers.
This visual brilliantly illustrates the core concept. Just look at how a scattered, totally unorganized handful of individual monomers on the left inevitably change together into that massive, organized, snake-like polymer structure on the right. That single transformation right there, that's the heart of everything we're covering today.
So, the absolutely crucial point to remember is that nature and industry really only have two ways to build these massive chains. The first is addition polymerization. This is where your monomers are unsaturated and virtually nothing is wasted. The second is condensation polymerization. This one requires monomers with two different functional groups, and it actually ejects a smaller molecule, like a little byproduct, when those blocks link up.
Visually, here's exactly what you need to look out for on your exam papers. For addition, you're scanning for that carbon-to-carbon double bond breaking open so it can link arms with its neighbors. It's 100% efficient. But for condensation, you're looking for a snap-and-release mechanism where two blocks join together and kick out a small molecule, which is usually water, right at the linkage site.
Moving on to Section 2, the nylon blueprint. Let's look at a classic case study.
Building a super tough polyamide like nylon is actually a really straightforward three-step condensation process. So let's break down the exact sequence you're going to need to master for your structural drawings. Step 1 requires two distinct puzzle pieces. First up, you need a diamine, and notice its nitrogen-heavy amine ends. Second, you need a dicarboxylic acid, which proudly features its OH groups at either end. These are our starting blocks.
Now, in Step 2, the condensation magic actually happens. To forge the link between these two blocks, we strip a hydrogen atom right off the amine group, and we pull the hydroxyl group, the OH, off the diacid. We eject them together as a water molecule, H2O, to clear up space for the brand new bond.
Finally, they snap together to form an amide linkage. Now, take a really close look at the edges of the structure. Here's a pro tip for full marks on your exam. Always remember to draw your continuation bonds passing straight through those square brackets. Seriously, it proves to the examiner that you know the chain doesn't just mysteriously stop there.
Section 3, biodiesel from fats. Let's talk alternative energy.
Okay, what could greasy leftover cooking oil possibly have to do with the fuel inside a car engine? Sounds crazy, right? Well, it turns out the exact same functional group chemistry that builds large plastics can actually be run to transform messy kitchen waste into high-grade vehicle fuel.
Look at the complex molecule we have here. Vegetable oils are essentially heavy triesters. But by reacting them with methanol and throwing in a potassium hydroxide catalyst, we aren't building a longer chain. Instead, we're breaking them apart right at those ester linkages.
This specific reaction is called transesterification, and it beautifully snaps apart that heavy fat to yield three highly combustible, completely separate biodiesel molecules. It just goes to show that knowing your ester linkages isn't just some textbook theory. It is literally the key to engineering renewable alternative energy. And finally, Section 4, the polyethylene paradox. One monomer, so many different uses.
Take a look at this data.
We've got different types of polyethylene, and they are all made of the exact same ethene monomer. Yet high-density polyethylene, or HDP, has a softening temperature of 130 degrees and a much higher density. Meanwhile, low-density LDP softens way down at 90 degrees. So, how is that even possible? Let's look at how this actually builds structurally.
The secret lies entirely in the physical shape of the chains. Look at LDPE. It has these bulky carbon side chains branching off, which physically push the molecules apart from one another. Now look at HDPE. It's strictly linear. There are absolutely no branches, which allows those chains to pack tightly together, kind of like dry spaghetti inside a box.
That tight packing in HDPE leads directly to more mass per unit volume. Because the linear chains sit closer together, they generate much stronger intermolecular forces. And this structural closeness is exactly what makes HDPE harder, denser, and way more heat-resistant than the branched, flexible LDPE that we use for everyday things like plastic bags.
And this brilliantly illustrates why we leverage those exact properties in industry. We take that dense, unreactive polyethylene layer and we use it as the perfect waterproof shield to line the inside of iron food cans. It acts as a permanent barrier, so the iron doesn't react with the water or the acids in our food. Pretty clever, right?
But, mastering this toy box comes with a pretty stark, sobering realization. These incredibly strong, unreactive bonds that make our materials so durable, well, they are an absolute nightmare to dispose of. Because they're non-biodegradable, they persist endlessly in our landfills. And actually, if we try to solve that by burning polymers like nylon, we just end up releasing a massive footprint of carbon dioxide directly into the atmosphere.
Which leaves us with this final thought. We know exactly how to snap these molecules together to build incredible infrastructure, packaging, and fuel. But the ultimate test of our chemistry going forward won't just be building an indestructible modern world. It's going to be figuring out how to sustainably take that toy box apart. Thanks for joining me on this explainer, and go crush those exams.